Hey folks, George Leoniak. I'm just hopping on here real quick with another sacred geometry video here, new geometry. And the previous video I did was on the Earth grid. And, as it usually goes, the day later, I have a new discovery in regards to that. And I'll also clarify some things in that video. I discovered that in the end, there were these 61 great circles updating Buckminster Fuller's 31 great circles. And then I realized that I've left out quite a number of circles, which actually makes the total of 81 great circles based on the kind of vector geometry that I was using, which I believe is related to the Earth grid, as I've been discussing in the previous two videos. So I want to just describe in this video how I got there and what are the 81 great circles about and how were they formed. Okay, so let me, I've got a video here to show, not a video, a slideshow. So I'm going to share the screen, and it's a short one, I think. We've only got 9 slides today, but I think it's important to clarify this because I'm about to move on to a whole new subject that was kind of born out of this. But I'm excited to get there, but I want to just wrap this one up before I move on. So this is some images from my previous slideshow, the Earth grid one. And I have I have a name for this now, which I'm going to be calling the Geohedron, Geohedron, because I believe it relates to the Earth grid. And this is not showing, whoops, I believe this is all linked. Let me ungroup it. This is not showing the great circles themselves. This is just showing the kind of vertices that are associated with these points. So this is a 15 hoop model, and this is on the Google Earth. And this one here is one that I devised and overlaid over top of this, which rounded out all the previous vertices from the rhombic trichontahedron, et cetera. You'd have to see those previous videos. So hopefully if you've seen those, you should follow up with those after you see this or watch them prior. But yeah, so the main thing I do want to get to, and this is still from the previous one, I haven't drawn one with the 81 great circles. It's adding an additional 20 circles, but I'm going to describe where those circles are. But this is just showing the overlay of the 61 great circles and how they associate to the vertices of the geohedron there. So this is how I got there. What I discovered was this disdyakis dodecahedron, which is connecting to. So there's going to be 5 of these disdyakis dodecahedrons in this disdyakis trichontahedron. Now, this disdyakis trichontahedron is giving us 15 of the great circles, and the remainder of the great circles are going to be coming from this one. But the thing I realized in the video, and I'm going to walk through these in the next few slides, is that this one right here, this, when I was looking on the Wikipedia site for this form, it only described it as having 9 great circles. So I just went with that. And I realized that they're missing 4 more circles, great circles. And so, but prior to that, I was just going with the 9 great circles. And we have 61 total after I did this math to deduct the 15 from the 45. So I came up with 61 total, or adding 30 great circles to it. So, I realized, the next morning after doing the video, I was just visualizing the cubeoctahedron, because the way I went about constructing this, and I'll show you in the next couple slides, is that there's a cubeoctahedron, a cube, and an octahedron that are forming this. So the cube and the octahedron are providing some vertices, but there's also a cubeoctahedron. Now, this is a spherical version of it. And here is the same sphere. This is the cubeoctahedron underneath this, that the vertices are connecting. This kind of little arc here is kind of going across the vertices, and that's the closest point to create those. So that's really what geodesics means. I know I also came up with some great things on geodesic domes, Um, when we use the word geodesic, at least in geometry, it's related to the closest uh, point, a curving line from the closest points on the surface of the sphere, and then you're connecting those points as you go. And this is the way that Buckminster Fuller originally started getting involved with geodesics, and then the name got adopted to the geodesic dome, which was based on subdividing the triangle and pentagon faces. And then the underlying geometry, which I'm really focused on, wasn't as much apparent in those geodesic dome structures, which the geodesic is kind of added on to that. But really, the real description of geodesics has to do with these vertices and creating these arcs. So we're looking at, in what I'm working on here, the underlying structure and the geometry underneath these. So if we were working with the disdyakis dodecahedron as it is on the Wikipedia site, essentially, the same lines are there, these vertice points are here, but I believe that they're sunken in, and this is what I was talking about with the rhombic tricontahedron, because they're not biscribed as they are in the disdyakis dodecahedron that I'm working with, which means that these are similar, these biscribed forms, just to reiterate this from the last film, that the biscribed means that there's both a inner sphere that's going to touch all the faces of the form, and an outer, circumscribed sphere that's going to touch all the vertices. And there's only a handful of 8 forms, 4 forms and their duals, so that's a total of 8. And the other forms that do that are the platonic solids. So in my view, these 4 forms, this disdyakis dodecahedron and the hexahedron, the triakis dodecahedron. I'm getting the names mixed up right now. Excuse me. We have to check out that other video. They're important forms because they have that biscribed quality, which is related to the platonic solids. So anyway, this one is 13 great circles because we're adding in these additional 4 cubeoctahedron great circles. Without those, we do have 9. But I came to this realization, but before we get to that, I want to show you that Buckminster Fuller, this wasn't a form that was not on his radar, let's just say, because him and Charles B. Ryan here back in 1960, 1963, well before I was born, were constructed this form of 13 great circles. So it's always exciting and kind of reassuring to me in my own exploration of geometry, as I just visualize it, how I go about it. All of a sudden, I'm like, wow, I just constructed this thing that they did in 1960, 1963, which means that, just through my own explorations, I'm coming up with similar discoveries. I believe I went about it differently than they did in how they finally construct the 31 great circles. And I'll show you my reasoning for that, because I am basing everything on the internal geometry, which is giving you these vertice points. And I'm not really quite sure. They have a tetrahedron in here, which is, of course, is part of the cube. And I do see a cube in there, but they call basis on the rhombic dodecahedron, which means that these outer, these diamond-shaped faces here, these 3, this will actually give you like a spherical projection of a rhombic dodecahedron. So there's quite a bit of work, especially done with the Earth grid, that's looking at how all the platonic solids and other forms are like spherically mapped on the surface of a sphere. And I wasn't really interested in that, although now, after having that perspective and window open up, I can see where those forms are on the spherical projection of the form. I was really interested in the underlying geometry, which is like poking up the inside of the sphere that's giving you those vertices. And if you take forms like a cube or a octahedron and increase them and lower them in size, increase or decrease them in size, so all the points meet on the edge of the sphere, then that's really where I was interested in my exploration. But here's this model that they did, which is essentially this. In this one, I actually switched views. I was kind of going on a edge view before, and this is now a vertex view, which is based on like the seed of life drawing, which helped me actually see this. And this is what led to the discovery. So I was, working on these drawings because this is now describing, visually showing you what I was just describing. Is, I broke down the disdyakis dodecahedron into these three main elements here. We've got the octahedron, which was providing 6 of the vertices. So these little dots here, the blue, the black, and the red. I like creating these little dot diagrams because they kind of remove the lines and just show me what's on the surface of the sphere. Even though this looks like, and this has always been an optical illusion that I've been interested in looking at platonic solids or any form inside a sphere, it's not actually touching the outside of the sphere. It looks like it's just floating in space. But these vertices here are touching a √3, which is this, square root of 3. All these measurements, I like the base on that measurement because it's based on a 1-inch cube. So for instance, the 1-inch cube, this is a cube that has a 1 inch. But if you took and measured this edge here with your ruler, it would be, I think, 1.81 or something like that, or 1.86. I forget the exact value, but it's less than 1 inch. So, that means that this is now sunken down into this sphere here, which the internal diagonal of a cube from one corner to the opposite corner, like a Merkaba, for instance, if it's a 1-inch cube, has an internal dimension there of √3. And that's what I'm basing this outer sphere on. And there's a cool thing about the cubeoctahedron, which, I didn't really recognize, but when we put it into this view, it actually, all 6 vertices around this of the classic hexagon shape are all touching the outer edge of the sphere, which is √3. So of course, this is a hexagon and all these are touching this. So the sphere is the appropriate size sphere for the vertices to be touching the outer edge, because it's 1.732 √3 across this dimension here. So I was doing this drawing and looking at that, and I was like, wait a second, I didn't include these vertices in the vertices of the cubeoctahedron in my original assessment. Like, I didn't do the geodesics of that. I didn't kind of connect the dots to draw in the hoop, that great circle that would connect over from here to here to here to here would be one circle. I didn't include it. I just followed these lines that are part of this disdyakis dodecahedron. So essentially that reduced 4 vertices, 4 great circles for those 5 cubeoctahedron that were represented in there. So there should be 20 additional great circles, is basically what I'm saying. Here's what the kind of fusion form of these 3 are. And, you might look at this and be like, well, how do you draw this? Is this just, how is this sacred geometry? Am I just in some mathematical, program that just does this all for me? And, I'm leaving out the sacred geometry and just playing with these shapes. Well, I just want to reassure you that I spend a lot of my time, and this is how I make my discoveries and interest in this, is really trying to find ways to connect this back to the sacred geometry so that we can draw these things. We can include this in our art and in our science, and show that sacred geometry is this bridge between these two, and that the scientific validity of it is just as great as the artistic expression that you can utilize with this. But then it's like, well, how do I then draw the 48-faced, disdyakis dodecahedron from that seed of life view? And I'll show you this little image at the end, but this essentially, I got creative and I like to color these in. Here's the disdyakis dodecahedron right in the middle. And I'm showing here that we have the seed of life that it's based on. And then I found all with this little diagram here, which I'll show you in another video how that's constructed. But this is presenting all of the vertices that we need. Now, the thing is about the seed of life and even the flower of life, which I'm going to really dig into in my next videos. If you're interested in learning more about the seed of life, flower of life, what it can and cannot do, does it contain all the platonic solids? What does contain all the platonic solids from this view? How do you draw it that way? I'm going to really work that out and show you that this form right here really opened up my eyes. Drawing it this form, this disdyakis dodecahedron, allowed me to make discoveries about the platonic solids that I didn't realize I was going to make. But so, we've got the 1.73, we've got this other measurement here, which is square root of 6 divided by 1.5. It's a really important measurement that I work with a lot in the circle, in the seed of life. You've got your octahedron that's going to be in here. But essentially, within this little diagram, I'm giving you all the vertices that we need by placing a cube in here and getting that last one. You see the vertices are lining up at those nodal points. So I can do the cubeoctahedron. There are the vertices for that. I've got the cube vertices. I'm getting those through the dotted lines here from the outer edge here. And I'm getting this from the inner sphere that's in here. Now, that's the same size sphere that the actual seed of life is constructed on. And then within that, I've got within the cube that's contained within that, I've got the inner one, which gives me the little triangle that you need for the cube to finish the drawing of the cubeoctahedron. So, to me, it's really important, as I'm stating before, to figure out how to draw this with sacred geometry, or else I feel like I'm just kind of just playing with the power of the programs to like computer program or the apps or whatnot to just do it for me. And in doing that, I feel like I'm missing out on something and I'm missing some discoveries. And I feel like maybe that's why I'm coming up with, why I've chose a different approach or come to a different approach of how to see how those three forms, the cubeoctahedron, cube, and octahedron, form the underlying vertices of this shape, because I'm figuring out the internal structure that it's full. There's other forms in there rather than it being, completely empty space. And then just focused on the outside of the surface. There's the internal structure there. So, okay, this is kind of the summary of the slides with this disdyakis dodecahedron. Now I've switched our orientation here to the square view, I sometimes call it. So instead of being in the vertex seed of life view, this is now how I did most of the drawings in the previous video. This is as if a square and a cube is just a flat square. So this is the original disdyakis dodecahedron that I showed you that had 9 great circles, and I've upgraded that to the 13 great circles. And you can see that these little arcs here are now providing the vertices, which would be inside the cube, which is presenting those that are of the cubeoctahedron. This is the disdyakis dodecahedron, the 48 faces that it has. It has 26 vertices, and that is, fits over top of this here, like so, providing the new vertices. And then I just wanted to double check, if I put this new one over top of the disdyakis tricontahedron here, that's the one that's going to provide, the 15 great circles. I just wanted to double check to make sure that my cubeoctahedron vertices are not going to be deducted from that, because the regular disdyakis dodecahedron, which had the 9 great circles, 3 of those circles were already included in this one. So now what I have to do is I have to deduct just 3 from the 13. So now I'm going to have the 10 great circles of the disdyakis dodecahedron. So we got 10 left. And let's just see, we've got 15 great circles, 3 times the 5. So that's the 15 for the disdyakis trichontahedron. So I've got 13 times 5. So I've got 5 of those. Remember, the form that I created, which I'll show you in the last image, which they're calling the geohedron, is the has got 81 great circles now, but it has 5 cubeoctahedrons, so it's got 5 disdyakis dodecahedrons in it. So that means there's 5 of them kind of oriented to the shape of a regular dodecahedron, the 12-sided dodecahedron, because that has 5 cubes in it. And you'll see this in my other video. I show you that the dodecahedron has 5 cubes if you're not aware of that. So if there are 5 cubes in it, that means there's also 5 cubeoctahedron, and the fusion of those forms with the cubeoctahedron and the octahedron and cube, those all combine together to create this 13 great circles times 5. So that gives us 65 circles. But remember, 15 of those great circles are already part of this disdyakis trichontahedron. So we reduced that, and we got 50. So now we're at the 31 great circles, which was Buckminster Fuller's kind of last big form that he was working with geodesics in this way, the 31 great circles. He's done one on 25, which was all based on the cubeoctahedron, but 31 was kind of the max one. And I just included with the cubeoctahedron, the different way of formatting than he did with the 25 great circles. But I've included an additional 50 to add our grand total to the 81 great circles based on all the information that I've applied to this, which is including the dodecahedron and the icosahedron and the dodecahedron, which are all part of this form here. So all the vertices include all the platonic solids, and this is the final view of this one. Let me zoom out just a bit. I think I have the naming of it. Yep, there's the geohedron, the 81 great circles, the geohedron. So I think, well, let's see. We'll christen the name here, geohedron. We'll add it to the library of names. Add geohedron. All right, it's official. Geohedron's been added to the book, so when I type it in, it won't have the red line underneath it anymore. So anyway, I have fun just naming these things. It helps me relate to it. But remember, I feel like this pentagon structure with these pentagonal faces here, this has 20 subdivisions on each pentagonal face with the pentagram in the center, and subdivided again with the cubeoctahedron. This will present 240 faces plus the 81 great circles, and has 120 vertices. And 120 is another number that I'll be getting into a little bit more because it's shown up in another area on a flat polygon surface that is also related to this work. So I've got a lot more to share, but like I said, I wanted to do a kind of quicker video on this, just to wrap up where I'm at now with the Earth grid, and based on the research that I've done. And but where we're going with this is, like, yes, I'm going to do more on the 120 side polygon and the associated angles with that, which are also related to the platonic solids. But before we wrap up, I just wanted to show you this one a bit closer. This is in the center piece here. That is that disdyakis dodecahedron right here. So that's got 48 faces when it's a full form. I really like, with my form of drawing and artwork, is to find ways to draw these as blueprints that contain a shape that you could basically pull off of this, because it contains an actual form in there. And that's where I'm going with the platonic solids. That's supposed to be with the flower of life and all that, to show us the geometric structures in there, and we want those to be accurate. If it's not accurate, we've got to figure out ways to upgrade and change that, which I'm working on. This here is this this has got the 13 great circles. So, you know, I started off, just did the 9 great circles, and then this added this. This is actually like the second or third little structure I made. You know, when I saw the cubeoctahedron, you know, I saw that you could just put circles around it. So I just made this and figured out the flow of the crisscross of the patterns of movement around it. So, you know, this has got 9 plus this. So this form, when we're looking at it, just like this here is, you know, adding this to the 9. So that's the 13 great circles. I really enjoy making these little structures afterwards, just to see if the page, the 2D that I'm doing, shows up 3-dimensional, because like I said, this is a template, a blueprint that contains the actual forms. Now, the 240 face form, that took a lot of effort to figure out all the little mechanics and drawing and getting all the shapes to the right size. We could do it by hand for sure, but the accuracy might start to deviate with so many lines over time. But this one was quite easy to draw, and I'll probably do a video on that. So anyway, I hope you enjoyed that follow-up. And I'm thankful I get to share this, and I hope you are enjoying speculating and thinking about the 81 great circles, or more inspired to check it out, how it relates to the Earth grid. And like I said, I got more great content coming, and I'm looking forward to the next time. So much love to you, and peace